In a previous video, I defined sine of z and cosine of z, where z is the complex number x plus iy, in terms of its real and imaginary parts. In another video, I also defined cotangent of z in terms of exponential functions. Cotangent of z has a restricted domain, which comes from the fact that you can't divide by zero. In this video, I would like to define cotangent of z in terms of its real and imaginary parts, which uses the previous definitions of sine of z and cosine of z. I'll link all the relevant videos in the description. So cotangent of z is defined as cosine of z over sine of z, just like in the real numbers. To define cotangent of z in terms of its real and imaginary parts, we need to plug in the definitions of sine of z and cosine of z in terms of its real and imaginary parts. If we do that, the expression becomes cosine x cosh of y minus I sine x sinh of y over sine x cosh of y plus I cosine x sinh of y, since cosine of z equals cosine x cosh of y minus I sine x sinh of y, and sine of z equals sine x cosh of y plus I cosine x sinh of y. The next thing we need to do is to multiply both the numerator and denominator of this expression by the complex conjugate of the denominator. So we need to multiply both the numerator and denominator by sine x cosh of y minus I cosine x sinh of y. And if we do that, we end up with this huge expression. I would like to do a few things now. If we factor out a sine x cosine x from the first and fourth terms in the numerator, and also factor out I sinh of y cosh of y from the second and third terms, the numerator becomes sine x cosine x times cosh squared of y minus sinh squared of y minus I sinh of y cosh of y times cosine squared of x plus sine squared of x. In the denominator, we can rewrite the cosh squared of y term as 1 plus sinh squared of y using the hyperbolic identity cosh squared of y equals 1 plus sinh squared of y, and the denominator becomes sine squared of x times 1 plus sinh squared of y plus cosine squared of x sinh squared of y. Cosh squared of y minus sinh squared of y equals 1, and cosine squared of x plus sine squared of x also equals 1. So the numerator greatly simplifies to sine x cosine x minus I sinh of y cosh of y. In the denominator, if we expand sine squared of x times 1 plus sinh squared of y, the denominator becomes sine squared of x plus sine squared of x sinh squared of y plus cosine squared of x sinh squared of y. If we factor sinh squared of y from each term in sine squared of x sinh squared of y plus cosine squared of x sinh squared of y in the denominator, it becomes sinh squared of y times sine squared of x plus cosine squared of x. Sine squared of x plus cosine squared of x equals 1, so the denominator just simplifies to sine squared of x plus sinh squared of y. We can simplify this expression using some trigonometric and hyperbolic identities. We can rewrite sine x cosine x in the numerator as 1/2 sine of 2x, using the double angle formula for sine, and rewrite negative I sinh of y cosh of y as negative 1/2 I sinh of 2y, using a hyperbolic identity. In the denominator, we can rewrite sine squared of x as 1/2 minus 1/2 cosine of 2x, using the power-reducing formula for sine, and we can also rewrite sinh squared of y as negative 1/2 plus 1/2 cosh of 2y, using another hyperbolic identity. The 1/2 and negative 1/2 in the denominator cancels out, so the entire expression simplifies to 1/2 sine of 2x minus 1/2 I sinh of 2y over negative 1/2 cosine 2x plus 1/2 cosh of 2y. If we multiply both the numerator and denominator by 2, we get sine of 2x minus I sinh of 2y over negative cosine of 2x plus cosh of 2y. If we split the expression into its real and imaginary parts, we end up with sine of 2x over negative cosine 2x plus cosh of 2y minus I times sinh of 2y over negative cosine 2x plus cosh of 2y. So this is the definition of cotangent of z in terms of its real and imaginary parts. So the definition of cotangent of z in terms of its real and imaginary parts is cotangent of z equals sine of 2x over negative cosine 2x plus cosh of 2y minus I times sinh of 2y over negative cosine 2x plus cosh of 2y. We also need to keep in mind the restricted domain. Cotangent of z is defined for all complex numbers, except for k pi for all integer values of k.